I have no idea if this technology is going to work, which, if it did, it just got recorded. Um, so, of course, I didn't charge everything, so I don't get to walk around as much. But in theory, we're now recording lectures, and annotation, whatever's up on the screen, should get recorded, and then I'll post it into Canvas, and hopefully it works. We'll see. We're going to double back to worksheets in a second. Specs quizzes. Residence is usually the one that calls everybody out and usually starts dropping this kind of question out there as in a request for more time. Not necessarily for more attempts, but we'll talk about that too. What is the intent of the specs quiz? It's a hard question. Yeah, it's to assess mastery. Okay. If you have more time, or let's switch that, change that around a little bit, does mastery involve time? Whether you want to like that or not, yes, that is absolutely true. This is why when you go to the doctor and they're like, oh yeah, we'll see you, and then they call you back in 6 months and say, hey, we think we've got some drugs that might help with those symptoms, you're going to find a different doctor, right? That doctor clearly doesn't have mastery of their subject if they're waiting 6 months to get back to you. Okay, so time is a necessary part of mastery. Most of this is intended to be self-assessment of mastery, and that gets a little bit gray as far as self-assessment because it's being graded through Canvas. But it gives you the opportunity to see how well you've mastered that individual topic. Okay, so first attempt, you should have gone through and attempted, say, 9 specs quizzes at this point. Okay, which is not true for the entire class. There's about half the class that hasn't even attempted them yet. Okay, that's kind of okay. Just realize those are going to start to pile up on you real fast. And those are setting you up to point out whether you actually have mastery or not. Why does it become important to have mastery of those topics? Add them on to new topics. We don't even have to worry about that yet because there's another thing that gets in front of us first. Exam 1. Exam 1 is where now I will assess whether you have some level of mastery within that topic. So if you aren't testing yourself along the way to figure out where your mastery is at, when you get to the exam, what you're going to find is you don't have mastery of any of it, and you're going to have a real hard time being successful in the exam. Remember, the original intent behind these assessments was that students had 5 weeks to go through and complete them, and if they did not complete them within those 5 weeks, they were told to drop out of the class, period. Like that was it. That's how this is being used from the original source material. Okay. I think that's harsh, personally, and so we use it as kind of a guide to help you assess along the way with how you're doing with that content and where you're at. Okay, because it is all too common and easy to go through and just Google an answer. Oh, I have an answer to this now, I can move on. Okay, that doesn't prove that you've actually assessed any mastery, and when you get to the exams hurt that much more. Okay, so the point in the specs quizzes is to push you on that, which is why the request for time sort of unfortunately falls on deaf ears. Okay, not entirely, because when I initially put these assignments out there, the time was half as much as what you currently have. Okay, and so the first wave that went through said, this is absolutely ludicrous, there's no way we can do this. And so I doubled that time. Okay. The quizzes have some conditions associated with them. One of them is that a time limit must be enforced within it, okay, which is why you're getting that double time as it is. Because I do feel that some of them were a little short, to put it mildly. Okay, but the intent again is that you should be finishing these in about half as much time as you're actually assigned. Okay, for the record, there have been a couple people that I've commented on that have gone through and done it, and I said you should slow down. Okay. And why should they slow down? They're submitting it early and getting something wrong. Okay? If you have the time, take advantage of the time. If you don't have the time, you're already taking advantage of the time, that's fine. Okay? Kind of makes sense? More attempts. Absolutely. I have no problems giving more attempts. The first 3 attempts are effectively free. The 4th and subsequent attempts after that, you get progressively more and more intervention from me. Okay, so what I'm going to do is reach out and say, you're not getting this concept. Have you done this practice yet? So for this 4th attempt, For you to get access to this fourth attempt, you need to prove that you've done this practice. Here's a place that you can do some practice. Show me your notes. Okay? And then I'll look at the notes to get a feel for how you're doing with it. Because maybe when I look at your notes, I'm like, you really don't understand this, and I actually need a one-on-one intervention with you to say, this is what we need to fix. Okay? That's not bad. If anything, that's a good thing. You get that targeted advice to make sure that you can actually be successful later on. Okay? And then I'll progressively open up those attempts. Kind of makes sense? Some of the assignments, which we'll get to in a little bit, I will probably just tell you, just do all 3 attempts. Just do them, and then I'll give you credit for it at the end of it. Okay, and that's one particular topic that I wouldn't be surprised if we got questions about today. Next question on this is notes or not. You're not being monitored for this, so you're welcome to use your notes. Okay, I don't have any problems with that. Just realize again that short time means if you're going in with the intent of using your notes, you better have your notes handy and ready to go. Not, I'm going to start, oh, maybe I should pull out my notes. You're wasting time. Okay, kind of makes sense? Okay. It is a self-assessment, so again, you could decide whether or not you wanted your notes. Okay, maybe you really want to test, I think I've really got this down, I don't want my notes handy. Okay, that's fine, do that. You have control over that. Kind of, sort of? Okay. With the specs quizzes, as I go through and look at them, and believe it or not, I am looking at them, I will post to a general announcement category saying, hey, these are the common mistakes that I'm seeing. Okay, so I've done that with, I think, 3 specs quizzes, maybe 4. Okay, they're usually small things that are just tips that people just aren't quite aware of yet, and that's because you haven't really mastered it. That's okay. So probably review that announcement. You'll probably actually see comments from me of, hey, you should go look at that announcement because you're making those mistakes more than likely. Make sense? I went through and looked at what you should have done today. So I didn't carefully look at the specs quiz due dates though. The lecture videos for this week, according to the timeline, which makes me think there's a typo, all should have been watched for this whole week by today, which I thought was kind of shocking. The reason that went through my mind is I would argue some of the content in this is kind of hard to manipulate and for students to understand. So I want you seeing it so that we're talking about it in class sooner rather than later. Okay, the hybridization and ultimately molecular orbital theory usually throws students for a loop. So if you're on top of it, we can have that conversation sooner rather than kicking that later and later in the semester. Make sense? Worksheets. So in the past, I had created these worksheets. So I'll go ahead and show these. I've got a couple examples here. The intent was it was a flipped class. We'd come into class, and instead of me doing any lecture, it was all just worksheets. You would just work through worksheets on your own. What I found is that it ended up being more work. The whole point of the flipped class is not to add more work. It's to maintain the same level of work. So if we do the same level of work, and then I say, and you now also have to do these worksheets, that was doing more work. So I removed the worksheets from the course. I do have several of them. I can publish these and make these accessible if you want. There's at least a couple head shakes, yes. I'll try and make a module page that just links out to all the worksheets that I've got, okay? In the case where we don't have questions, these are things that I'm pulling up and being like, what questions did I like within that I think that I'm seeing as common patterns, and so I'll pull to these in and of my own as well. Make sense? Okay, so I'll try and remember to make sure that those go public. I believe they're numbered based off of what week. So yeah, I think worksheet 2, oh, never mind. Literally says week 2. Yeah, so I'll try and get those all posted so you've got access to them and we can kind of spin through some of that. So worksheets covered, specs quizzes covered, lecture videos, logistics questions. Anybody have any logistics questions? Nope. Okay, which puts us into kind of 2 categories that I would kind of hesitate, as you'll see in a second, to talk about. The topics that kind of came up this week through the lecture videos were nomenclature. Okay, as a past, at least one of your colleagues started that assignment, and then hybridization and molecular orbital theory. I think hybridization, molecular orbital theory are much more interesting than nomenclature. And you might be able to tell about the typo written within nomenclature, my opinion of the nomenclature concept. Okay. Um, None of my stories are short. Short story, I actually, part of being part of the district, proposition's the wrong word, but we're going to use that, propositioned all the colleges to say that we need to abolish nomenclature from organic chemistry. That was legit, full on. I just went in straight because we were updating competencies. I said, this needs to disappear. It should not be in any of our competencies, knowing full well it was going to cause an explosion. And it did. The very next meeting, I had 3 people come sit down next to me, and they're like, so, we would like to have a conversation with you. I was like, okay, what's up? Like, why do you want to get rid of nomenclature? And I was like, nobody learns it. It's not useful. We should get rid of it. They're like, well, how do you talk about any of your chemistry? I was like, well, how do you talk about it? So, well, I point to the structure. I go, guess what I do? I point to the structure. They're like, well, but naming is so important. I was like, okay, how well do they do on any naming? Oh, they're awful. I think you're adding points to why I'm winning and you're losing this conversation. But ultimately, nomenclature is this kind of big, hairy mess. The way it is presented to students is that there is one name for all chemicals and that's it. Okay? And as you learn through Gen Chem, that's perfectly true. All chemicals have the exact same name. So sodium chloride, when you go to the store to add that seasoning onto your food, it says sodium chloride on the label. Right? No, it doesn't. What does it say? It says salt. Okay. Naming, right? You learn some naming. Let's do some simple naming here real quickly. Let's see if this works with me. Cool, right? You know how to name that compound, right? How do you name that compound based off the rules that you learned in Gen Chem? Dihydrogen monoxide. And that's what we refer to it as, right? And all we refer to it as water. Okay. Unfortunately, naming as a system came about with a good reason and a good intent, is to enhance communication. Okay, because somebody came through calling that water, somebody else called it agua. Right? Oh, those can't possibly be the same thing, they have different names. So we tried to come up with a standardized name. That's nomenclature. That's the intent behind nomenclature. So we have a standardized language to communicate. Okay? Except that when we talk about dihydrogen monoxide, you will find a huge population of people thinks calling it dihydrogen monoxide is tedious to label all those pieces out, and so we'll instead refer to it by its common name, water. Okay? And all those people are like, well, that's tedious, I don't want to do that. You still have to communicate with, which means as a student or as anybody in the field, not only do you have to understand the absolute end rule for how to name, you also have to know how all the old curmudgeon-y people refused to change call it. Okay? So every single compound that you will encounter has more than one name. And that is insanely frustrating. Okay? So the rule sets that we get you try to narrow the field. And so theoretically we say, okay, yes, this is a mess. So we'll tell students they're only responsible for IUPAC names. Okay, so IUPAC, the International Union of Pompous, choose your own A, curmudgeons. Okay? So they went through and they would look at a structure and they would be able to come up with a name. At least one of you has experience with something along these lines. So we would go through and look at the name for this structure. So the first process within our naming, okay, there's rules, okay, and there's a slide that I start nomenclature off with. Those rules, that page, you need to know, okay, because if you know that, you can get your way through most nomenclature questions. Okay, will you be able to perfectly name a compound? No, but if you call me Mickle, I'll probably respond because it's close enough, right? From Michael. Okay, so that's all you need when it comes to nomenclature. Can you get close enough to be correct? So our first rule set is I delete. How did I, what? That doesn't even make sense. What just happened? Okay, maybe the technology is not going to do what I want it to do. Our first rule set would be to identify the main chain. The main chain needs to be the longest continuous chain of carbons. Okay, so what I would recommend you do if you're trying to do this by hand, my handwriting looks so much better when I could zoom in. I just need to get over that loss. Is highlight that main chain. Okay, there's no other chain that I could identify or circle or color in that would get me a longer sequence of carbons. Okay, how many carbons are in that main chain? Okay, and if you're struggling on that, right, this is, people were kind of upset with this comment because I said counting is hard. Bro, counting is hard, period. Okay, and anybody that thinks different is fooling themselves. Okay, this is why we count 1 through 10 and then we created powers of 10 so that I didn't have to count higher than that. Okay, that's the whole point, is to avoid counting higher than that. So you said 8, so we could go through and we could call this you fucking shithead. Oh, I can scroll. Wow, I can scroll. Maybe this is fun. Maybe I like this. Stop jiggling. Okay, just stop touching it. Okay, 8 carbons. Okay, calling it 8 carbons sounds weird, so we want to come up with a high-powered name that allows us to kind of reference it really coolly. So was it Greek? We'll use our Greek prefix. What's our Greek for 8? Oct. So we'll call this oct. Okay, referencing how many carbons. So it's oct. I now also want to reference some information about that backbone. I want to reference that those are all single bonds just to carbons. There's nothing fancy in it. Okay, so to do that, that's where we would talk about our hybridization, okay, which is why hybridization comes up in this unit. What? Why'd you delete everything? Like, that was rude. I said I was going to do it. Let's try it. It's not acknowledging. Hey, I'm touching. Okay, I can erase it. So there's oct. Is it there? Oct. And I want to talk about its hybridization. I'd really like to color code this. So the hybridization is what's going on in that backbone. There's nothing interesting going on in the backbone. So the nothing interesting functional group is known as an alkane. Alk is referencing our carbons, just single carbons, and the ane is actually our hybridization. So we'll call this oct. I don't care because it's organic, it's going to have carbons. So I'll drop the alk and I'll just include the hybridization part, which is ane. So I get oct ane. That's exciting. Okay. Has this name now covered everything within the structure? No, it's missing something. What it's missing is what we would call the substituent. So we now need to figure out what's going on within the substituent up there. Okay. So how do I want to deal with that substituent? Well, what I want to talk about is how many carbons are in that substituent. Just like I did with the main chain, I want to find the longest carbon chain. So what is the longest carbon chain? No, that's a different question than we started with. The longest carbon chain in that substituent. Okay, so we're getting 2 answers, which is great. We're getting 2 and 3 because some people are going through, I can't zoom, stop it. 1, 2, 3. I can undo, right? I don't know how to undo. Okay. Other people are going through and counting 1, 2. Right? So who's correct? And how do we decide who's correct? We have to establish a rule set for how we address this. Okay, what is the rule set? You start your numbering from where it connects to the main chain. That's our rule, which means the people that said 1, 2, 3 are wrong because I don't have 3 carbons in a chain coming off the backbone. I only have 2. Okay, but that sets up a new dilemma for us. I cannot zoom. If you see me like doing this with my fingers, just chime in. Why did it change font size? But whatever. I have 2 carbons there. I need to name those 2 carbons. Well, what is 2 carbons? eth. So I can call that an eth. I could start to think about, well, what's the functional group in that? Well, if there's no functional group, there's nothing exciting within that. So I go, oh, it's ethane. The ane is an ending. That's the end of my name. This eth isn't the end of the name. It's a piece on the larger structure. So I don't want to end it with the ane. So what I'll end it with is a different term that allows me to know, is it because my other hand is touching it? That it's a piece. That piece is the YL. So cool, I'm getting some more information in here. So I'm saying this is an ethyl octane because there's a 2-carbon piece connected to my octane. But where is it connected on the octane? Okay, that now becomes a challenge because I need to make sure that I specify where on that chain. Okay, so one option is I just put numbers down on this and we go through and deal with this. So let's just do this in black. So 1, 2, 3, 4, 5. Okay, it wasn't picked up for the microphone and probably the majority of the class didn't hear it, but one of your classmates said that it was connected at carbon number 4. I'm saying it's connected at number 5. Does that mean there's 2 names? Because if I draw out 8 carbons and connect at carbon number 5, aren't I going to draw the exact same thing that one of your classmates is going to do when they draw out 8 carbons and connect to carbon number 4? And then one option is, nope, you're totally not going to do that. What's my name? Yep, that's a legit question, not rhetorical. Mike, cool. What is it now? Careful. It's still the same name, right? So picking up and turning the structure doesn't change its name. So when they went through and counted it, they counted not left to right, but right to left. So they achieved that coming in at 4, not 5. How do we decide what's right? Well, do organic, well, does anybody like numbers? No. So what do we choose to do? Pick the smallest possible numbers possible. So when I went through and numbered 1 through 5, I numbered incorrectly. Even though if we did 5-ethyl octane, we could draw the structure, that name is invalid because I didn't follow the rules. I mean, nomenclature is just rules. That is literally all it is. A group of people sat down and said, what is the rules for how we do this so that we get one name? And they screwed that up. Okay? So it's not 5. That ethyl is located at position 4. Don't use your fucking fingers. Give me my pen. Okay? So I'm going to say that ethyl is located at position 4. Okay? Note, I didn't just write 4 comma ethyl, I wrote 4 dash ethyl. Does that change the meaning? Unfortunately, yes. Are there spaces in there? No. What happens if you include a space? You're wrong. Okay? Particularly if you're taking like a specs quiz and you're trying to nuance all these individual pieces. Okay? Because that's what nomenclature is. Okay? So 4-ethyl octane, cool. We got lovely numbering. We've said what the substituent is. We labeled it. We've got the octane. Have I identified all of the atoms? Remember that little stinking little black thing right there? So no, I haven't labeled all the atoms. There's another thing in there. Okay, and I'm out of color options. Right? Oof, as I color over it. There was also something right there. Well, how many carbons was that? That was 1 carbon. 1 carbon we'll call meth. Okay, so now what we're going to have to do is identify that meth. Sounds a little bit silly. Okay, it's a substituent again, right? So we have to call it methyl, YL. Okay, where is that substituent located? Because I have to tell you where it is. We need to know the locator. Where is it located? On the ethyl, cool. So we're going to have to be important with that, but where on the ethyl? The 1 position. The 1 position was by definition where it connected to the main chain. So we have 1 methyl. Cool. Is that one methyl the one on the octane? No, that's the one on the ethyl. So now we have to be extra careful to make sure that that methyl is not connected to the octane, but connected to the ethyl. Well, how the hell can we do that? Dash, unfortunately, doesn't do it. We need to make sure that these two things are grouped together. And how do we group things? With parentheses. So I can go through and say parentheses, 1 methyl. What is that 1 methyl connected to? The ethyl. Should I include the 4? What does that 4 mean? Fourth position, it's the location of what? Of the ethyl on the carbon backbone. Right? So if I put the 4 in the parentheses, I'm going to lose its meaning. So I need that 4 because that's referencing the substituent. That 4 needs to go all the way out because what's the substituent? It's the 1-methyl ethyl, which I just gave away some of that. So I'm going to put a 4 out there, okay? And then I'll put the ethyl here. Okay? That 4 is telling me parentheses is located at position 4 on my octane. What is parentheses? The parentheses is 1-methyl ethyl. You confused enough yet? Because I think it's fucking ridiculous. Okay, but now I got to put this all together again. I need another parentheses here. Note I wrote the 4. Dang, when I write numbers, what shows up next? A dash, which means if I write 4 here, I need a dash. So what am I? Wrong. I leave that dash off and the whole thing falls apart. Okay, so I have 4 parentheses, 1-methyl ethyl, end parentheses, octane. And now I've got that whole structure together. Do you like that naming with the parentheses, the 1-methyl ethyl? No. In fact, most people hate it. Okay? In fact, organic chemists for a long time have decided that that nomenclature system is stupid and they want a new system. So what did they do? They switched to common names. You mean like water? The whole reason we weren't going to do this? Yeah. Yeah, exactly. So what they went through and did is that when we had substituents like this, we decided that 1-methyl ethyl was too problematic, and what I'm going to do is call 1-methyl ethyl something else. The one person I provided feedback to might know what that name is. Do you know? Did I provide feedback to you, or did you just figure it out? Oh, okay. It's isopropyl, and then the YL because it's a substituent. So what does our name become? 4-isopropyl octane. Okay? That 1-methyl ethyl part, we just ignore because I don't like that. That was too much work. You either do it or you don't. It's this half-assed nonsense that happens in organic nomenclature that I think is why it should be abolished. Or one of the reasons why. Okay? Problem with the specs quiz? You are responsible for IUPAC. You are not responsible for common name. The specs quizzes use the common names for the substituents. Which means what's going to happen when you go through and take the specs quiz on nomenclature? You're going to get it wrong. Okay? This is why I would probably, and so the first person that did it, I went through and looked at it because they were like, I need help with this, figure out what's going on. Because there's a shit show of numbers and dashes and spaces floating through that. And if you screw up any one of those, the whole name is wrong. Okay? And since it's graded all or nothing, you have no idea why you were wrong. So they asked for targeted feedback. I provided targeted feedback. And again, there's so many different things that could go wrong. It becomes really hard to help that particular individual. Okay? So I could call out certain things, and then other things I tried to talk through with this 1-methyl ethyl. And in theory, they were probably, oh, this makes a lot more sense now because that typed thing was nonsense. Could be wrong. Okay? But that was probably what's going through their head now, I hope. Okay? Kind of makes sense? Okay. So, you want big picture. Their mistakes that they made for that particular individual did have some content lapses that I've got problems with. They pulled the crappiest pull that they could get because they had two structures that they had to come up with names with, and both of them used isopropyl. Sucks for them. Okay. But they made some other mistakes too. So I tried to help them, and I haven't gone back to see if they've gone through and attempted second and third time. Okay. But their second and third attempts, whether they get them right or wrong, I will probably go in and just manually give full credit because they have enough stuff that's right that I can kind of guide and say, I think you're good enough. You can pass nomenclature without a problem. Does that make sense? So of our specs quizzes, we talk about mastery, mastery, mastery. Nomenclature is not mastery. Okay? And I swear to God, I hope none of you become masters of nomenclature. Okay? And it's certainly not because of anything I do. Okay? That you became a master. If you suck at nomenclature, that is totally on me. Yes. Okay? Kind of get the idea and the flow for what's going on within it. So nomenclature, when it comes, is going to be frustrating. Okay? And invariably, online homework systems, okay, I've seen it all over the place, will ask about rules that are not identified in your textbook. Why? Because there's a lot of rules. Literally, the rule book for organic nomenclature is larger than your textbook. We're talking larger dimensions, onion leaf paper, and font size like 5. Okay? There's an absurd amount of rules behind how you deal with nomenclature. You are going to get things wrong. Okay? Get the big picture idea, you should be good. Why? Because I'm not going to test you on do you know the name full out. What I'm going to test you on is multiple choice. And what I'll do is call attention to the common mistakes that are those big picture ideas. Okay? And you can call me out back. Be like, dude, this test question asks for way more details than you said you would ask. Okay, you win. You probably won't, but it's worth a try. Kind of makes sense? Can we stop talking about nomenclature? Okay. I almost guarantee we're going to get more questions on nomenclature. It's okay. I will talk through them. I know a surprisingly stupid amount of nomenclature. Okay. Which would then take us into hybridization and molecular orbital theory, which I have no problems talking about because I think that's particularly fun and exciting. That's probably why I'm standing up here and you're not. Those topics in and of themselves aren't super, super critical. You could probably stand to miss a significant chunk of points on those and still do very well within the class. Okay? But when it comes to a question of why, almost invariably the why comes back to hybridization and molecular orbital theory. Okay? So if you're trying to figure out long-term patterns, molecular orbital theory is worth a sit down at. Okay. Questions? What do you want me to look at? That was the stuff that I saw, and if you give me free reign, I'll open whatever I want. Do we always use the number before we have anything? Okay, so start off, it's nomenclature, no. 100% no. It is never always. It is never always. Okay. Officially, when it comes to nomenclature, we're supposed to follow certain rule sets. You can do what I want? Okay, looks like it's doing what I want. So let's switch to a slightly different structure. Let's try the whiteboard. Let's get rid of words. I don't know. Is that black? Looks like black. We'll make it a little bit more challenging. Oh, we'll just make this one not only challenging, but also frustrating at the same time, because why not? So let's go through and try and process this name together. What's our first step? Count the number of carbons. Okay, so we want the longest, wait. Erase. I want black. Let's do that. Okay, now back to your statement. We want to find the longest carbon chain. Okay, so think about it. Identify the longest carbon chain. For the record, a lot of people are drawing. That's cool. You can draw that out. I did say just think. Okay. But now I got to think about it. Okay. What is the longest carbon chain? All together in unison, it is? No. It's not 7. He did say counting was challenging. Maybe he just can't count. No. Okay. Those people that watch the video might have a slight step up on this. Okay. You're not strictly tested on it, and I don't think the video actually pushes through something quite as advanced as this, but the rule sets are actually stated within that. Is the rule find the longest carbon chain? That's a hard question. Is the rule find the longest hard carbon chain? It is continuous, yeah. That contains the highest priority. Okay? What priority? What? Functional group. Okay, you remember how we have to know our functional groups? We have to be able to go through and look at this and say, where is the highest priority functional group? Because that highest priority functional group has to be part of my longest carbon chain. So for those people that said 7, you probably counted just kind of straight across, left or right, right, left, I don't really care. Okay, zigzaggy all the way across. But when you do that, is the oxygen counted in that backbone? It is not, which means you haven't accounted for the highest priority functional group. The highest priority functional group is the alcohol in this chain. That would be the OH. Okay? This is why understanding our functional groups becomes important, or knowing our functional groups before we start with nomenclature becomes a big deal. How do we know what the priority system is? Somebody sat down and said, ta-da, this is the priority system, and you now have to have it memorized. Yet more things that you have to memorize. This is, again, why nomenclature is freaking stupid. Okay? Generally speaking, the more chemistry involved with the functional group, the higher the priority. Well, what do we mean by chemistry? Being able to, why would things react? Think about it differently. Do I have electrons? Yes. Does the outlet have electrons? Yes. But if you touch me, you're not going to die, theoretically. It depends on, I should not have picked that as an example. Okay? If you touch the electrical outlet, that's dangerous. Why? It is the electrons that have the ability to flow. Okay? It is effectively charge. What's coming out of the electrical outlet is a buildup of charge, and that charge is tunneling to hit a ground state and become neutral. Okay? I'm mostly neutral to begin with. Okay, right? I'm not an excited state. Okay? So how could I look at a structure and decide if it's charged or not? This is all Gen Chem now. What? Okay, so we could look at, let's say, an example. How do I know that one's charged? Oh, we see the negative in the, you're like, this is dumb, Mike. Is this one charged? Now we hit a little gray area, because when we do that, you're like, oh, it's not charged, because I don't see a charge in the upper right-hand corner, and yet, what is sodium chloride made of? Sodium plus and chloride minus. You mean a cation and a chloride ion. When you look at sodium chloride, you recognize that that is an ionic bond. And because it is an ionic bond, we have ions, and it is therefore charged. Those charges are inherently potentially reactive. And so we want to neutralize them. How did they become charged? Because if I take sodium, it's not charged. And I take chlorine, it's not charged. When I put them together, how did they become charged? We transferred electrons from one to the other. Okay? And because there was a full transfer of electrons, we called the connection between them an ionic bond. Cool. Are there other bonds? Yes, there are other bonds. What other bonds are there? Covalent bonds. So when we're first introduced, it's ionic and covalent, which is cool. The ionic were all the metal and nonmetals, and then the covalent were all the nonmetals. Okay? And if we look at the nonmetals, they connect, well, they're sharing electrons. And because they're sharing electrons, do they ever generate a charge? No, which means do they interact? The whole point of charge is that we want to cancel that charge, so they would react. If we don't have charge, they don't react. So all covalent compounds don't chemically react? No, that was false. Okay, so how could they possibly react if they don't have charge? The second part comes in. It has to do with their sharing of electrons. Okay, when we talked about ionic and covalent, we looked at that covalent, it's not just that they equally share electrons, they can unequally share electrons. And when they unequally share electrons, they generate partial charges. And those partial charges can now chemically react because I want to neutralize that charge. And when we looked at the previous structure that we had with all the carbons and hydrogens, all of those bonds would be known as what kind of bond? Carbon and hydrogen. Covalent. And this one, our alcohol, that OH, what kind of bond do I have between the O and the H? Polar covalent. There's a difference in electronegativity because there's difference of electronegativity in the polar covalent bond. That makes it, by default, higher priority than all the other species. So now I know I have to name this compound according to that structure. I need to find the longest carbon chain that contains that alcohol functional group. That longest carbon chain is going to turn this direction. Difference in electronegativity, yes. Okay, it gets a little bit more complicated than that because there's a lot more complicated functional groups out there. Okay, but that's a decent starting point as far as nomenclature goes. And I would argue you don't need anything more advanced than that. Okay, so we can now look at it. How many carbons do we have? We have 6. 6 carbons is hex. Okay. I heard a couple of saying adding hexane. Okay, I might have even heard a hept. Hept is 7. I don't want to add the ane yet because the ane was the functional group. Previously, the ane was functional group of the backbone. There was no functionality. Here, I do have functionality, so I have to address that functionality. But I also simultaneously want to address that that backbone has no functionality. So what we're going to do is a couple things here. Number one, we are going to take advantage of that ane, but just a little bit. We're not going to end it. I'm going to say AN. This AN is now saying my carbon backbone is all single bonds all the way through. Okay, outside of my functional group. But now I have to call attention to that extra functional group. What is that functional group? Okay, cool. Alcohol. Okay, the alk, again, carbon. So what part of the alcohol do I want to include in there? Should I call this hexanalcohol? Like, no, that sounds stupid. Instead, I can call it hexanol. That's now my backbone. Okay. Your question was about numbering. We're going to get to that. I promise it's there. Okay. Where do I want to start my numbering? The highest priority functional group is going to kick this off. So my numbering is going to start 1, 2, 3, 4, 5, 6. So where is my alcohol? Where is that OH located? It is located at position 1. So I could call this 1 hexanol. And so far, all I've identified is what's in the red circle. Do I have anything else floating in this? Yes, what else do I have floating in this? I don't think I meant to be that irritating of a substituent, but you know. Hey, yellow doesn't show up too bad. I've got a substituent. Okay, within that substituent, I technically have a substituent on the substituent. This should look familiar. What does that substituent look like? Isopropyl. So I could go through and call this isopropyl because I'm now familiar with it. Where's that isopropyl located? At position 2. And I have 2 isopropyl, whoops, P-O-R-P, assuming I spelled this backward, trying to minimize spaces, and I get 2 isopropyl 1 hexanol. Cool, that name is acceptable. What does IUPAC say about it? Is wrong. Why is it wrong? It's not clear enough. Why is it not clear enough? What is that 1 referring to? Is it referring to the hex? The hex was the main chain. It's not referring to the hex. What's it referring to? It's referring to the all. So IUPAC goes through and says that proper name is actually 2 isopropyl, oops, I don't even need a dash, we can run them together, hex and 1 all. Is that fun to say? No, which is why the vast majority of organic chemists say the top one. So depending on which rule set you follow, you get a different name. You angry yet? Because you should be. Okay? The process is still all built there. When it comes to how we go through and name, that's the process I want you to think through. Find your longest carbon chain, that contains the highest priority functional group. Identify what your functional group is. Identify the number of carbons in that piece. Identify where that locator is. What if you have multiple substituents? Then you have to organize the multiple substituents. You would have to name each of them. You would have to locate each of them. And then you would have to put them into the name. Does the order in which you put the substituents matter? Of course it flipping does, because that's the point, is to come up with one freaking rule. So what's the order? Alphabet. So you have to organize your substituents by alphabetical order. Okay? What do you have 2 substituents at the same location that have the same name? Let's go at position 5. Let's make life miserable, right? Everybody loves misery. That's why you're in this class. I go to position 5. I know that looks like a curve. It's supposed to be 2 straight lines. Those are both methyl groups, right? So I could call those a methyl. But how many methyls do I have? 2, so I could call it methyl-methyl. That sounds silly. So instead I'll call it dimethyl. Where are those methyls located? Position 5. So I'm going to say at position 5 I have 2 methyls. That's what this language means. No, you have to tell me exactly where each substituent is. This is not 5-dimethyl. This is 5,5 dimethyl. Every single substituent must get an identical or get a locator. Now, which comes first? Isopropyl or dimethyl? Dimethyl because D comes before I in the alphabet, right? Is the D the substituent? Yeah, the D is not the substituent. It's the methyl, it's the substituent, which means, which comes first? Isopropyl, then the dimethyl. And you're like, this is stupid. How am I possibly ever going to know any of these rules? If I have anything to do with it, you won't. Okay? What's going to happen is you're just going to have to practice and kind of get used to these, and you'll start to notice the patterns, and it will just sort of naturally come in. Okay? Nomenclature is something that I do not feel is high value. Okay? Couple stories, backstories about me. First time I took OChem, I withdrew from OChem because I was failing the shit out of it. Okay? And said, there's no way I'm going to pass this class. I'm very stubborn and no motivational skills, I would argue. And so I would just take it again. So I took it again, but the second time I changed my approach. Okay? And instead of just doing, I'm just going to write as many questions as possible, I shifted my focus to what do I think is most valuable? Okay? And the things that were valuable, I spent time on. And the things that I didn't think were valuable, I didn't spend any time on. I didn't spend any time on nomenclature, which means every time it showed up on a test, I skipped it. When did I skip it? Instantly. That's naming. Next question. Okay? That meant I acknowledged a complete and utter loss of those points. Okay? That was my choice. I would argue you need to do the same. You have to decide where it's best to figure things out, because some people will be great at nomenclature. That's awesome. It's gonna suck. I'll tell you why here in a second. Other people will be great at other aspects. Okay. But nomenclature ultimately doesn't have a whole lot of value to this class. If you know how to name this compound when you leave this class, I would be irritated. But if you understand how that compound could potentially chemically react, that's huge. Now I'm happy. That's a big deal for wherever you're going. Okay? Because everybody needs that knowledge for your target. That's important. Okay? That's the critical piece. So when it comes to nomenclature, what do I do to fix this? Well, back to that second time I took it, I did fairly well. I got an 89%. 10% of the class was nomenclature. Effectively perfected the entire class except nomenclature. That was my own fault. I didn't do it. I got a B. Fully accept. That was my choice. Okay? I don't want that happening to other people. Nomenclature is stupid, and I will say I'll never swear again. That's not true. Okay? It's just dumb. It does not make up 10% of the class. Okay? And if you can figure out the basic patterns of what I've discussed, you can reason through your way any nomenclature question for that very specific purpose. Does that kind of make sense? Yes.
So in real life, you would think that structures are a lot more complex than that, hundreds, thousands of chains long. Are you really going to name something with all those?
Which is the other part of it, yeah.
That seems absolutely ludicrous.
Yeah, which was the argument that my colleagues came back to me with. It was like, but when they go to grad school, they'll have to name all the compounds. I was like, really? What was one compound you synthesized? And they're like, well, I can draw it for you. I was like, I know, you can't name it because you don't know how to name it. It's like, well, I did learn how to name it. How did you learn how to name it? Oh, I drew the structure into the software and it told me the name. You mean you didn't learn nomenclature? And every time it was like, but they still need to do it. I get it. I get it. Still dumb. The point is communication of knowledge. We invented nomenclature so we could communicate knowledge from point A to point B relatively quickly. As long as everybody knew the rules, they could draw the structure. But now what can we do? Draw the flippin' structure and mail the picture of the structure. Not even snail mail, like email. Okay? You could probably be in a live chat and draw the structure with them instantaneously. Like, you don't need nomenclature. Can we talk about something else? Okay, what else do we want to look at? Yes. Clear. Erase. Ooh, cool. C2H2? That's not at all what you asked me to do. Let's try that again. So C2H2. So first thing we should be able to do is to draw out a Lewis structure relatively quickly. This becomes a bit obnoxious because we're looking at a condensed formula. So this is one of the things that I try to push early on is formulas are useless and we should get out of formulas and get into structures relatively quickly. With a little bit of practice, hopefully what you would notice is your best structure is going to be this. You also listed through that it involved a bunch of counting, and it is quite possible that I entirely counted wrong. Okay, that's not C2H2, that would be C2H4. C2H2, let's try this again. Triple bond. Okay. So what we want to do is address all of the kind of scenarios between these. So when we're talking molecular orbital theory, what are we looking at? Okay. What we're saying is that the atomic system fails, but we know there's some truth behind it. So somehow the atomic system has to come together to make the molecular system. Okay, so if you really push this, you get the linear combination of atomic orbitals, which is where it's usually pushed to the extreme when we talk about computer modeling and all of that. So we're taking atomic orbitals and we smash them together to see what's going on. So let's take a look at what's happening with this first bond. Okay, so what is happening with that first bond? What atomic orbitals are involved in that bond? It is an S bond. When you say S bond, S bond gets me a little bit nervous. I wouldn't actually call it an S bond. I would call it a sigma bond. Okay. Why is it being called a sigma bond? Okay. And so this is why using S bond is kind of okay. We're getting a sigma bond because the orbitals being used to make said bond are all S-type orbitals. And for the sake of the recording, we're using massive air quotes around S-type. Okay, so what are the orbitals coming from the hydrogen? S is not an orbital. S is an orbital type. What is the orbital coming from hydrogen? S is half right, if that makes you feel better. Okay, that hydrogen is contributing the 1s orbital. That's what it's contributing to this system. What's the carbon contributing? And we're about to make a giant leap if you haven't seen any of the hybridization theory stuff. Okay, so what I just heard from the crowd is that that carbon is contributing 1s2, 2s2, 2p2. Yeah? Okay. That's what the carbon atom is contributing. Do I have a carbon atom anymore? No, unfortunately that carbon atom has been morphed into a new species. That new species is now in this mix somehow. So somehow those atomic electrons have to be rejiggered so that it can make this compound. Okay, and this is where hybridization comes in to help us out a little bit, because if we're going to look at this structure, what bond angle would I predict around that carbon? 180 degrees. This is going back to 151 with our Lewis structure. We have two groups of electrons that has to be 180 degrees. What is the bond angle between two p orbitals? 90. So if I was just going to use the atomic orbitals, can that explain the bond angle I'm seeing here? That's not going to work. Okay, so I can't use atomic orbitals to explain the bonding pattern behind this. So what I have to go through and do is say, well, what electrons of this electron configuration are the most relevant for me? Say again? I don't know what that means. Which of these? Oh, never mind. Totally hear you now. The valence electrons. What are my valence electrons? The outer shell, the outer energy shell. The outer energy shell is identified through that number being the 2, which means these are now my valence electrons. Those are the only electrons I'm going to predict at a first approximation to contribute to this bonding system. Those electrons have to somehow reconfigure themselves so that they can get 180 degrees between them. How could I possibly go through and do this? This becomes a whole lot more complicated to mathematically draw out, but what we're going to end up doing is taking all of those orbitals. Okay, well, wait a sec. That says 2s2 and 2p2. What are the orbitals that I'm talking about now when we look at those electrons? So when I say 2s2, 2p2, there's just an s orbital and a p orbital, and we're done? SP2 or 3. I like the hedging. Okay, when we talk about the s orbital, how many s orbitals are there for a given energy level? Just the one. How do you know that? As a hint, I'm standing in front of the board that might be relevant. Helium has 2, but it still only has 1 s.
Because we can fit only 2 electrons in 1 orbital?
2 electrons per 1 orbital. So when we talk about the s, when we take a look at our s block, remember, knowing our orbital sections was useful. The s block is just those first 2. There's only 1 orbital because each orbital can hold 2 electrons. And if we talk about the p block was this section. So you're telling me because I'm now p, I can fit 6 electrons in an orbital? That would run counter to there only being 2 electrons in an orbital. So what happened when I moved to the p? What's that?
Did it hold 3?
Nope.
6 electrons?
How is that p orbital holding 6 electrons? We just said a p orbital can only hold 2 electrons. How can I possibly, say again?
There's 3 of them.
There are 3 p orbitals. So when we're looking at our atomic structure, this is our mix. We're taking all of those and we're trying to figure out how we can mix those in to get a system behind this. And I just lied, this one's actually perfect for this. Okay, well, what do those things look like? What does the s orbital look like? Circle. What does the p orbital look like? Dumbbell. You said dumbbells, plural, because we've got the dumbbells up, down. We have the dumbbell, cool, left, right. And then we have the dumbbell that I'm not going to be able to draw, but we'll pretend I'm good at 3 dimensions. Okay, we'll call that y, x, and z. Is everybody okay with that? Okay. Are y, x, and z absolute truths? No, those are completely arbitrary. We're just putting a label on it so that we have a way to communicate with each other where they're at instead of saying the up, down one, left, right one. Okay? So let's say, for the sake of the carbon, I need to generate some orbitals so that I can make this bond. Okay? I need to take these orbitals and I need to somehow create it so that I have 2 groups of electrons. 1 group on the left, 1 group on the right. Okay, so 2. What do you think is going to happen if I take all 4 of them and mix them with each other? How many new orbitals should I get? Should I get 6? Why should I get 4? That's a really hard question, mainly because we're talking about probabilities here, but we're going to pretend about some of this stuff.
Because
What?
of 1 s and 3 p.
And what do those represent?
Places where the electrons could be.
Not just places, but in particular.
Electron cloud
And what's associated with that electron cloud?
to make bonds.
The first row is called something, the second row, third, fourth, those are all the energy levels. And according to the conservation of matter and energy, when I put energy together, I can rearrange it, but I can neither create more nor destroy it. So if I take 4 energies and mix them together, what do I have to produce?
4.
I have to produce 4 energies. Okay? Do I want 4 energies? I want 2 groups. That's what I want. I want a group on the left, a group on the right. That's all I need. Okay? So if I want 2 groups, how many of these orbitals should I take together? 2. So now the question becomes, which 2 should I mix? Why do I have to keep the s? As a hint, poorly drawn. I screwed something up in my drawing. Why do we have to keep the s? So we'll fix it. Maybe this will help as a hint. So our s, I screwed up the drawing. I did a horrible job with it. Here we'll go, we'll fix it a little bit. How did I fix it? We're talking about energy. So that when I go through and evaluate these, I'm always going to use the s because I'm always going to use the lowest energy first. So if I'm going to hybridize, we start with s, which means all of my hybridizations will involve some amount of s in them, which means all of those hybridizations should be classified as S-type. there's the air quotes. Anytime you have an s orbital involved, it's an s-type orbital. Okay? Or a sigma. What was the other type? Pi. And pi begins with p, which means don't use the s. What should you use? P orbitals. Let's cut to that in a second. So if we go through and process this, what do I want to hybridize with this s? The p. Which p? The y. Sure, fantastic. I love the idea. So let's take those two orbitals and let's mix them with each other. What happens when I mix this with this? Oh, the clouds. What does that mean? So electrons are able to collide. This becomes a challenging one because how many electrons are we talking about? How many electrons have I defined in my SMPs? I think I turned on a speaker. How many electrons have we defined? How do you know you have an electron? Nope. Because orbitals can exist and not have electrons in them. Does the hydrogen atom have the 7s orbital? Yes, it does. How do we know it has that? Because we can cattle prod it and it can jump to the 7s orbital, and when it falls back down, what does it do? It releases energy in the form of light, and we can now pick that up. So all the orbitals are already there. How do I know I have an electron in that orbital? What do I have to do to make sure that there's an electron identified in that orbital? I have to place it there. I have to draw it there. Have I drawn any electrons? No. So we are not talking about any electrons yet. Okay? What we are talking about is electron probabilities. Okay? Where we could see a probability of the electron having a positive amplitude or a negative amplitude. Why does that become important? What happens when two positives hit each other? Careful of waves when two positives hit each other. They actually increase. Okay? So if I take one positive and I overlap it with another positive, what happens right there? It doubles. It actually gets larger in intensity. Okay? And so when we looked at our s orbital, that sphere, what was it? Was it positive or negative? That one's tricky. It's simultaneously both, but uniformly, it's one of them. Okay? Are you optimists or pessimists? Optimists, so we will go through and define the s orbital as positive for the sake of this example. How is the p orbital different? Is it different? Yes. How is it different? There's a negative and a positive. When we're looking at the p orbital, we tend to draw them just as a dumbbell. You shouldn't be drawing them as dumbbells anymore. What you'll start to see is that one of them is shaded. What is that shading supposed to represent? That's supposed to represent one of the phases. Okay? And whether we call it positive or negative is again arbitrary. But for an individual p orbital, it has both amplitudes available to it. And as we switch from positive to negative, we pass through a point. So if I've got positive, here's my negative, well, that's a negative sign. What do I pass through in the middle? A 0 point where nothing exists. What do I pass through in the middle? That 0 point. Does the s orbital have that? Nope, it's uniform all the way across. So the p orbital has that inversion point in it. This becomes important because one side of it will be positive and the other side will be negative. Why does that matter? So again, we should propagate our shading further up to our top. We've got that positive and negative. Do you want the shading to be positive or negative? Positive? Okay. So now let's take a look at our new system. We're now overlapping these two wave things. When they overlap, they're going to interact either constructively or destructively, right? If they interact, let's take a look right here. See that little red space? What can you tell me about that little red space? How are they interacting? constructively or destructively? Constructively. Because I've got the positive, we decided was positive, and the S we said was positive the whole time. Okay, shading is going to mess us up on that. Okay, should have chosen better. Okay, which means we're going to see a doubling of the probability on that side of the dot. So if I'm looking at this interaction, what I'm going to see is a larger lobe up here from my dot. That became way too circular. I'm actually impressed with how circular I am. What about this area? That's now destructive, which means what happens to the probability of seeing the electron there? It gets really low, and we end up seeing something like this. Okay? That's if the s orbital was positive, but we said the s orbital could be positive or negative. If the s orbital was negative, what else happens? I'm going to get another interaction, and the other interaction is going to look like, what color am I in? Well, let's just guess. Where I can form a bond over here, lots of orbital space to make a bond, and lots of orbital space over here where I can make a bond. And how many bonds would that be? 2. I've created a directionality where I can now make bonds. Is that the directionality I wanted for my structure? This is making bonds on the y-axis. Where's my bond? On the x-axis, which means I overlap the wrong orbital. So what should I overlap? The x one, the one that's coming out. So if we're talking about what orbital overlaps with that carbon, what's the carbon contributing? Ooh, good catch. Okay, it's not an s orbital, it's not a p orbital, it's a new orbital. It's an sp orbital. I'm taking the s and I'm mixing it with the x, make a new orbital. That new orbital I'm going to call sp. Why? Because I took one s and one p. That just means sp. That's where it's coming from. That generates now a potential overlap. So now the sp orbital from my carbon can overlap with my s orbital from my hydrogen. And if we were going to draw those, we've got my hydrogen, ta-da, there, and we've got my sp more or less looking like that. So all we've done so far is made atomic orbitals. What do we need? We wanted molecular orbitals. So how do I make the molecule? I now take my atomic orbitals, and what do? I need to overlap them. Okay? But those atomic orbitals have also these phases associated with them. So when I look at that single hydrogen-carbon bond, I can bring those two atoms near each other, right? Erase some of the stuff down here. I can bring the atom there, there's my hydrogen, there's my sp, and they are now close to each other where I can generate an interaction in there, right? What if they're in the same phase? What would that mean about finding the probability of the electron between the two atoms? It's higher. And if I have a high probability of finding electrons between two atoms, what have I made? I've made a bond. Cool. Is that bond going to be higher or lower in energy than my atomic orbitals? Ooh, that's a challenging question, but think about it this way. If we look at the atom on itself, hydrogen, let's just say it has its one electron. Ta-da, one electron. It's chilling on the s orbital, all by itself. And now I go and make a bond. Where can that one electron now go? It can move around. It can move to the carbon. Are you lower energy when you have more space to exist? Or are you higher energy when you have more space to exist? Typically lower in energy when you have more space. And how do you know that? When you break the law, where do you go? Into a little 10 by 10 box, and you're not allowed out of it. Okay? Smaller space is higher energy. When we make a bond, we're allowing the electrons to exist in a larger space. That larger space makes it a lower energy state. So I could now go through and say, what is this going to look like cartoon-wise? Cartoon-wise, I'm going to get a lot of electron density now between the atoms, and I'll get this tiny little piece hanging out over here. This is going to be lower in energy. Okay, so this was atomic. This is now a molecular orbital, and it should be lower in energy. I've increased the probability of finding the electrons between there. The overlap that I made between these orbitals was a direct overlap. These orbitals are directly overlapping with each other. Because they're directly overlapping with each other, I want to name this as a unique type. Okay? To come up with that name, I look at the atomic orbitals, and I notice the atomic orbitals are S and an SP type, which means when I combine two of those S and S things together, I got this direct overlap. So I'm going to come up with a name for this orbital that will be based off of S. And since S sounds stupid, we call it sigma. And I now have a sigma molecular orbital. But this was assuming they overlapped in alignment. Did they have to overlap in alignment? I didn't say anything about forming bonds. There's no electrons. This is probabilities only. Did they have to come into overlap in alignment? No. Which means just as likely to make this sigma bond or sigma orbital lower in energy, I also have an equal probability where they don't come into alignment. And when they don't come into alignment, what's going to happen? It's going to have to go up in high, whoa, that's not the color I wanted. It's going to have to go up in higher energy. And what we'll see, and I usually screw up the color coding, so don't stress too much about that. What we'll see is there's now a space in between where the electrons are not allowed to exist. That's that point of that 0 point. What does this mean to our energy? Well, the electron was all happy in its little s orbital, and now we went through and said, nope, it can't be here. Is that higher or lower? That's higher in energy. Okay? And not only that, but we're now saying the electron is not allowed to exist in that space. Okay? Should that be making a bond? No. But is it still an interaction? Yes. So now I need to define this interaction. It is still the overlap of s orbitals. So it's still going to be a sigma interaction, but I need that sigma interaction to be not a bond. Okay? And I know that's a double negative. Okay? Because not a bond means they were never interacting. They're actively interacting with each other. So I need a new word. I want to describe this as a sigma interaction that is bad for bonding. So sigma bad. Instead, we call it sigma antibonding, or we usually use the asterisk. The antibonding orbital is an orbital. It exists. It is part of your molecular orbital diagram. So whenever you bring two orbitals in with each other, you will generate a favorable interaction and a disfavorable interaction. So every orbital generates a bonding and an antibonding. Every time. Okay? So if I want to go and look at all the bonding and antibonding interactions within this particular line produces a bonding and antibonding. What does this one produce? A bonding and antibonding. What does the bottom line in the triple bond represent? Bonding and antibonding. The next one up. Next one up. Okay? That's going to give me my sum total, assuming I can count, and maybe I counted incorrectly in the thing, of all of my bonding and antibonding orbitals. That's the number. Okay? When we discuss this, we're checking off orbitals, right? This red one was an S and SP. This one over here is S and SP. Actually, I want the middle one. S and SP for our carbon, right? How did I get the other two lines? The other two lines can't use the s orbital anymore because I've already used it. I've already hybridized it. What's left over of my atomic system? This is where, if we go back to our atomic system that we had down here, we use the S and we use the X to make the SP hybrids so that we had that 180 degrees. What was left over? A PY and a PZ. And if we go through and run this exact same analysis with that other carbon, guess what we're going to find is left over on that atom? A PY and a PZ that will perfectly align with our other carbon. What do I mean by perfectly aligned? That's a Y, right? Holding up pens for those at home. There's carbon number 1. Is that a Y? Yes. Okay. If we talk about overlap, okay, we're bringing these atoms close to each other until what happens? Careful. Until the s orbital overlaps. The s orbital was that big globby blobby shape, which means do the p orbitals ever overlap? Nope. But if they never overlap, can we make a bond? No. But what happens if we change our viewpoint? Do they actually overlap? Yeah. Yeah, they do overlap. They overlap in the other axis. But you're like, but distance-wise, guess what electrons do? Quantum mechanics. They've been brought close enough that the electrons can tunnel or jump from one orbital to the next. As long as we're close enough, which means we get an indirect overlap. That indirect overlap is known as a pi bond because it involves p orbitals. I apologize, I'm done. In theory, I'm done. I don't know how to stop this.